Our last topic for this unit on limits and continuity is called the intermediate value theorem. So we're gonna first just discuss what the intermediate value theorem is. We're not going to do a proof of it because it requires actually some higher math that we don't know. But it's pretty intuitive what it says. So the intermediate value theorem says that if you have a function that is continuous on a closed interval from a to b, so that's kind of like the hypothesis of our theorem here, is we have to have a function that is continuous. If it's not continuous, intermediate value theorem is not going to apply. Which means anytime we deal with the intermediate value theorem, we're going to have to first give a reason why the function is continuous. So it says if the function is continuous on this closed interval from a to b, and w right there is some number that's between f of a and f of b. In other words, here's f of a down here at the bottom and f of b up here at the top of our little continuous function. If w is some number between there, then it is guaranteed that there is at least one number c that's between a and b, that if I plug c into my function, if I find f of c, I will get w, right? And this is true for all possible values of w between f of a and f of b. In other words, all it's saying is if I go from a comma f of a to b comma f of b all the way up here without picking up my pencil, it's guaranteed that every single value between f of a and f of b is yielded by some c number between a and b, right? It doesn't guarantee that that's the only thing that'll happen, right? I might have some values up higher, right, that aren't between f of a and f of b, but still every number between f of a and f of b was obtained by some number between a and b. Okay? That's all this theorem is saying. That's the intermediate value theorem. And the conclusion of it that we usually use is that if f of a and f of b have opposite signs, in other words, if one's positive and one's negative, then there must be a number c between a and b such that f of c equals 0, or in other words, that there's a root to our function on the interval from a to b. So what we're going to do is we're just going to do a quick verification using the intermediate value theorem with a simple function. Then we're going to apply it once or twice, and then do one or two more little things with continuity, and then this unit will be finished. So we want to verify the intermediate value theorem on 0 to 2 for f of x equals negative x cubed. So the first step is always going to be give a reason why f of x is continuous on our interval. And it's continuous on the closed interval from 0 to 2, well, because it's a polynomial, and that's a good enough reason. Polynomials are continuous for all real numbers. That's just a known fact that you can use. So we know this is a continuous function. So what we need to do then is we need to figure out what f of 0 is and what f of 2 is. And so f of 0 is just 0. And f of 2, we'd get negative 8 for that. And so what we're going to say is that no matter what, if we choose a value of w between negative 8 and 0, so negative 8 is less than w is less than 0, right? Then that guarantees us somewhere down the line that the c value that we end up with is somewhere between 0 and 2, between our a and our b value. So we've got to find some way to turn w's between negative 8 and 0 into c is between 0 and 2. So let's see if we can go ahead and do that. Well, we know that f of c is supposed to equal w. Well, f of c just means plug c into your function. That'd be negative c cubed. So we can say negative 8 is less than negative c cubed. We'll replace w with f of c is less than 0. And now we should be able to just undo this inequality to show that c is going to be between 0 and 2. So we'll start by dividing by a negative 1, which will make this a positive 8, a positive c cubed, and a 0. But it will flip our inequality signs. And then we'll just take the cube root. 2 is greater than c is greater than 0. And that's it. It's been verified. That's the end of the verification. We started off with a continuous function. We showed that f of 0 and f of 2 were negative 8 and 0. And we said, well, if we pick any value between them, any w on that interval, it can be found with a c between 0 and 2. So now we're going to show that this function has a root on the open interval from 1 to 2. So in order to do that, we'll use the intermediate value theorem, which I'll sometimes abbreviate as IVT, intermediate value theorem. So we'll just start first off by saying, well, we're going to be able to use it because we know f of x is continuous on the interval from 1 to 2. Well, because it's a polynomial, right? And if it's not a polynomial, you got to give some other reason. Most functions that we'll deal with are continuous on their domain. So if you can just find the discontinuities and say, well, it's on this section of this domain and it's continuous on that section, it's usually going to be fine as long as, as long as you're not doing anything weird, breaking math rules or incorrectly figuring out where discontinuities are. It should be fine. So let's see what f of 1 is. Well, f of 1 is just 1 to the 5th, which is 1, plus 2 times 1 to the 4th, that'd just be 2, minus 6 times 1 cubed, that'd just be 6, plus 2 times 1, that's just 2, and minus 3. So if I go through all that, that's 3. 1 plus 2 is 3, minus 6 is negative 3, and then negative 3 plus 2 is negative 1, minus another 3 is negative 4. And then f of 2 should be, well, 2 to the 5th, that's 32, minus 2 times 2 to the 4th, that's another 32. That's just going to cancel out. Then we have minus 6 times 2 cubed, that's minus 48. And then I went plus there, 32 plus 32. Minus the 48, and then plus the 2 times 2 is plus 4, and then minus 3. So we got 64 plus another 4, that's 68, minus 48, that's 20, and 20 minus 3 is 17. And so we know that since 0 is, in fact, I don't know why I'm writing it quite like this. Let's say since negative 4 is less than 0 is less than 17, right? Then by the intermediate value theorem, there exists some c on 1 to 2 such that f of c equals 0, right? And so there is a root somewhere on this interval because our function went from negative to positive and it was a continuous function. And those are the two basic things you'll need to be able to do with the intermediate value theorem. Verify it, and then use it to show there's a root or that there's, some value of y on it. So we got two last little things that we're going to do here. First one is we're going to find all values of a so that f of x is continuous for all real numbers. So we should note that the only discontinuity of either piece of this piecewise function would be at negative 1, right, from the x plus 1 being in the denominator there. And so the only possible location of a discontinuity would be negative 1, so therefore it could be continuous for all real numbers as long as we can find this a value that makes both sides match up. So let's do our 3-point definition of continuity. Let's say, does f of negative 1 exist? And the answer is yes, it's a times negative 1 plus 5, or negative a plus 5. Okay. Second is, does the limit as x approaches negative 1 exist? And so that one we'll have to actually figure out. Well, the limit as we approach negative 1 would be everything when x isn't negative 1, right? So we just need to deal with this, x cubed plus 3x squared plus 3x plus 1 over x plus 1, which we should know that's just x plus 1 cubed over x plus 1. And so then if I just simplify that, I end up with x plus 1 squared, plug in the negative 1, and you get a limit of 0. So our limit is 0. Our function exists. We just need the two things to equal each other. So just set negative a plus 5 equal to 0, and you end up with a equals 5. will make this function continuous for all real numbers. And now we are on to our very last one here. This time we have to find all values of a and b such that this function will be continuous for all real numbers. Okay? So we've got f of x is 3x plus 5 when x is less than or equal to -1. It's ax squared plus bx plus 1 when it's between -1 and 2, and it's 3x when x is greater than or equal to 2. So I think we can tell for sure that at -1 and at 2, the function does exist, right? So really all we need to do is make the limits from the left and the right match up. So let's do a limit as x approaches -1 from the left of f of x and see what we get. Well, that'd be 3 times -1 plus 5. So that should be, well, -3 plus 5 is 2. And if we do a limit as x approaches -1 from the right of f of x, we should get, well, a times -1 squared plus b times -1 plus 1. Or in other words, we should get -1 squared is just 1. So that's just a minus b plus 1. And, you know, if we're trying to get the limit from the left to equal the limit from the right, we just need to set those equal to each other. So really we need a minus b plus 1 to equal 2. Or even more simply, just a minus b needs to equal 1. So that's a start. Then we're going to have to do the same thing with the limit as we approach 2 from the left and 2 from the right. So we'll do this on a new page. A limit as x approaches 2 from the left of f of x. Well, as we approach 2 from the left, that'd be ax squared plus bx plus 1. So I plug in 2 to that. 2 squared is 4. So I'm going to have 4a and 2b. So I'm going to have 4a plus 2b plus 1. And then down below, as I approach 2 from the right, it's just going to be 6, right? The limit as x approaches 2 from the right of f of x is just going to be 6. So we're going to have the limit as x approaches 2 from the right of f of x is just 6. Or in other words, 4a plus 2b plus 1 needs to equal 6. Or 4a plus 2b needs to equal 5. So now we've got two different equations. 4a plus 2b equals 5, and a minus b equals 1. So if we throw those in here, if we talk about, we got a minus b equals 1, and we've got 4a plus 2b equals 5. Well, it's just a system of equations that we can solve either using combination or substitution, your choice. I'm just going to multiply this first one by 2, giving me 2a minus 2b equals 2. And then when I subtract, or actually when I add these two things together, I'm going to get 6a, and then 2b plus negative 2b cancels. 6a equals 7, or a is 7/6. And if a is 7/6, well then 7/6 minus b is supposed to equal 1, right? If I just use a minus b equals 1, well 7/6 minus 1/6 ought to give me the correct equation. And so if we go back up here, that means that, in fact, let's open up Desmos here real quick. And we had our original equation was 3x plus 5 for x less than or equal to -1. So let's put that in. We put in 3x plus 5, and let's see here. That'd be when x is less than -1. That's going to look like that. And now that we've found our values of a and b, so it's 7/6 for a and 1/6 for b. So we'll have 7/6 x squared. And then what did we have going there? We had plus 1/6 x plus 1. So plus 1/6 x plus 1. And that was valid from -1 to 2, and ignore, I've kind of got the wrong inequalities there, but it doesn't really matter. I just want to show that it does match up here at -1. And then our last one was just 3x, and that was for x greater than 2. So if we throw in our 3x, and we just say that that's when x is greater than 2, we can see that that matches up real nicely at each of those 3 little points, or 2 little points at x equals -1 and x equals 2. Our function now matches up and is a continuous function for all real numbers. And so that is the last thing that you need to be able to do for this unit. That's the last lecture of this unit. And our next unit will be on derivatives, where we'll start off using limits and then move into a bunch more stuff with derivatives, where we can really get into calculus. But that's it for this unit.